Welcome back to another video on heat transfer. So we're gonna go ahead and solve this problem. Again, it's from the same textbook. So it says we have a large 5 centimeter thick brass plate of K equals 111. So heat is generated uniformly at the rate that they mentioned. And so one side is insulated while the other side is exposed to an environment at 25 degrees Celsius. They gave us the heat transfer coefficient as well. So the first thing that we're going to do is write down everything that we know. Okay, so we know K, which is that, and then we know that heat is generated uniformly at a rate of 2 times 10 to the 5. So E gen equals 2 times 10 to the 5 okay, and 25 degrees Celsius, and H is 44. Okay, so this is everything that we know. I'm also going to write to infinity equals 25 degrees Celsius. Okay, so here we have a T0, and then here we have a TL, because we're going to have two different temperatures, okay? And we have a intuitive thought that at T0 we're going to have a higher temperature compared to at TL, because this side is just insulation, right? So heat has no way to go, and then this side is just open to free air, and this is colder, which is why we're gonna have a lower temperature at TL. So okay, so we have that, and the question says that where in the plate the highest and the lowest temperature will occur. So just like we said, we know intuitively that the highest temperature will be here, right? So the highest temperature is here, and the lowest temperature will be here. Okay, so that's something that we have that we know intuitively. So now we're gonna write down the equation that describes almost any general heat transfer system. Okay, so this is the equation. E gen dot K equals 0, because we know that we have a heat generation. That's why we are keeping this one, and we're saying that it's a steady state, which is why we're saying that it's equal to 0, because it's a steady state. And also this one is one-dimensional, which is why we're only keeping the x here instead of writing the whole equation, which is x and y, z. Okay, so that's our equation, and we're gonna go ahead and solve this differential equation until we get to only t of x. Okay, so we moved this one to the other side, which became a negative, and then we integrate once so that we obtain this, right? C1 is a constant, so that's how we integrate once, and then we integrate once more to get tx, and this is what we have for tx. Okay, so that's our equation that defines this system. And now if you look right on this side, there is no heat flux, because all the heat that is being generated inside this thing, right, they're dispersing both ways, but they have no way to escape. On the left side, they have no way to escape because of the insulation. They can only escape on this side, right, which is why we have a lower temperature. So if they cannot escape, it simply means that at x equals 0, we have the heat flux, which is 0. Okay, so we're going to write the equation for heat flux, which is k dt over dx, and we said that at x equals 0, heat flux is 0, so at x equals 0, k is 0. Now if you want to say that q dot is 0, we can either make k equal to 0 or dt over dx equal to 0. Now we cannot make k equal to 0 because k is a constant and it's a property of the system. So the only thing that we can make 0 is dt over dx. So if we say that dt over dx is 0, then that means that q dot is 0, right? Because k multiplied by 0 equals q dot, which is 0. So that's how we verify that, okay, dt over dx is 0. So dt over dx equals 0. Now if you look from this equation, dt over dx equals, we said 0, right? And we see that it's equal to that, e dot gen kx plus c1, right? And at x equals 0, what does it mean? This is 0, so this whole term is 0, then it means c1 is 0. And at x equals L, we have T2, right? Or TL, which is we don't know yet, because we only know to infinity. We don't know TL yet. Now to get TL, we know that at this surface, right? At the surface, heat that is being conducted, right, is the heat being convected away. How do we write this? Well, we have the again, we have the equation, right, which is equals to h TL minus T infinity. Okay, this is the equation because we have conduction occurring to the left side and we have a convection occurring in the right side, and this is at x equals L. Okay, that's important. Okay, so we have that, and we already know dt over dx, right? And by the way, dt over dx is 0 at x equals 0, okay, not at x equals L. So from the dt over dx equals negative e dot gen over kx plus c1. We're gonna ignore c1 because we already found that c1 is 0, so we're not even gonna write it. Okay, so if we know this, we're just gonna write it here, negative k. So that negative and that negative cancels out, so we're left with k, and then e dot gen over k, and then that's x. Okay, so that's our dt over dx equals h TL minus T infinity, and we see that k with k cancels, and our x is basically it's just L, right? Because we're writing the equation at when x equals L. So now we know T infinity, we know h, we know e dot gen, and we know x. So the only thing remaining is TL. So we're gonna just go ahead and solve for TL. So TL equals to, we have e dot gen, right, times L, because our x is basically L because of that, and then divided by h plus T infinity. So this is the equation that will help us find the temperature at x equals L. Now we're just gonna plug in the numbers, okay? So e dot gen, which is 2 times 10 to the 5, L, which is what is, yes, 0.05 meters, divided by h, which is 44, plus T infinity, which is 25. So this gives us a TL value of 252.3 degrees Celsius. So now we know the temperature at L. How do we find the temperature at T0? Because they're saying that what is the value of maximum and minimum temperature. So TL is our minimum temperature, minimum or lowest temperature. So to find T0, we basically copy this equation, okay, and we just replace L with T0 equals T, instead of T infinity we write TL plus E dot gen L square plus 2K. This is the equation from the book, you can find it. So TL is 252.3 plus E dot gen, which is 2 times 10 to the 5, 0.05 square over 2K, which is 111. And our T at 0, which is our T maximum, equals to 254.6 degrees Celsius. So that's it. That's how we solve this problem. Thank you for watching. Write down your suggestions if you have any.